Today we are going to move into chapter 4, and I kind of want to bring the class into the center of our engine, which is our engine block. So we're going to center on that and have a discussion based on the pieces and parts that make up the cylinder block. That's not what I wanted to do. So moving into that, cylinder block, the largest single part of our engine. It's the main structure, it's the backbone of the engine, everything revolves around it. The main structure, it's got three main parts. The structure itself that contains the cylinder, pistons, all that kind of stuff. So the components, subassemblies are pistons, wrist pins, and the connecting rods. And then the bottom part of the block is going to be my crankcase. So I've done everything below the cylinders, the crankcase, and the bearings. And it does include the oil pan, because that becomes part of the structure. There are different types of cylinders, just like we have in the gasoline world. There are horizontally opposed. We have inline, which can be anywhere from 2 to
8 cylinders.
Yeah, and there's more than that in some of the bigger engines, so it can be a lot. They're all in a direct line, or some kind of V-bank. And a V-bank can be various degrees. So different manufacturers have done different things to kind of make the block tighter or narrower. They play with the balance of the engine. They play with lots of different things. And so the angle can change. The 60 degree is pretty common because it helps lend itself to smoothness of the operation. So that's a very common one. But they can be a lot of different angles. Just depends on what the manufacturers want. They throw a picture in your textbook about a Subaru. What's interesting is this is a Subaru 2-liter, and it's 145 horsepower. So it's an opposing. Pistons are going directly against each other, inherently very balanced, very smooth, low vibration engine. The next slide gets you into a Mercedes engine. It's just under 1 liter, and it's only 40 horsepower. So I find it amazing. The other one was 143. 145, and this one's only 40. But if we double the size of that, we're pretty close to the size of the other one, but the horsepower is different. So there must be turbos and some other things obviously involved in order to get so much horsepower out of such a small liter engine. So that's why I kind of left the 2 slides, and otherwise they're not that important. You can tell by looking at this picture, I have 3 cylinders all next to each other, so it's an inline style. I can tell that by simply looking under the hood.
It's a common rail.
Looks like it's going to be a common rail system because we have 1 rail that's feeding it. So there's some things that we should be able to start picking up when you open that hood. Another thing that these foreign cars like to do is you'll see there's 2 lines here that are clear. Volkswagen does that. And what's the purpose of these 2 clear lines?
Are those fuel lines?
They're fuel lines.
So it'll allow you to see if you're on a highway or diesel.
It would show you that, that's for sure. But most importantly, as far as the manufacturer is concerned, putting a clear line in there, I want to see if I have air bubbles. So you start seeing bubbles going through. So it's kind of a troubleshooting thing without having to add a line. They actually put that into the system when they build it. So my Volkswagen has a couple of these kinds of clear lines. So you put a filter in, you bleed it to the top, and then you start it up, and you can tell when all of a sudden the bubbles are gone. Right. If I had a line with a crack in it or something and I'm seeing bubbles in it, I could go find that problem. So it's just kind of a nice built-in way of troubleshooting. So I can't say that I've ever seen that on turf equipment, but it is a common thing in the automotive. It's pretty easy to add as long as the fuel line you're going to use is definitely a fuel line. You don't just get clear water tubing and add it in there. There is some newer EPA compliant fuel lines that are clear that would lend itself to this particular thing. This slide in here would lead you to believe that all engines are based on fan, flywheel. All number 1 cylinders start with the flywheel. We got Yanmars out here in our shop right now. number 1 cylinder is in the back of that engine and number 3 is in the front of the engine. So in the automotive world, this may be true, but in the outdoor power world, this is not true. And there is another brand besides GMR that also reverses the order and puts them in. One is near the flywheel and whatever the last cylinder is towards the fan. So make sure you do not assume that the order's wrong. The order is the other way. That's a bad assumption. So here's a International V8. So again, here's a manufacturer says here's 1, here's 2, 3, 4, and I've seen V8s where they go 1, 2, 3, 4, 5, 6, 7, 8. So you can't just assume that this is the way every V8's going to be. Always look at the manufacturer, find it in the book, find it somewhere. If you can't find it right up in the very front, another place you'll find it will be when you go to adjust the valves, because they'll tend to tell you where they are. So there'll be a particular place where it'll tell you finally where this is. So in the specifications, they might have firing order, but they may not tell you what number 1 and number 2 is. This is an Duramax. They have this scissor type cam gear. They don't really give me a good description of what this is, but this is some kind of vibration dampening cam gear to help take out some of the vibrations in there. And I don't have an answer to tell you how this actually functions. But it's just different manufacturers are trying to put items into the engine to help reduce vibration, and this is theirs. So we have an oil pump gear that's running down here near the bottom. We're going to be sucking the oil up. We don't want it to be a long ways. We have a crank gear directly attached to the crankshaft. It says upper oil pan.
Is it like a step down kind of?
So it may be one of those that goes and then it curves down. Sometimes you'll see an oil pan and then there's another piece. And it lends itself to different types of applications where you can change the volume. So they may have an upper and then they might have a lower one that varies according to application. So cylinder blocks, cast iron or iron is the most common. So some type of cast iron. They use sand casting. Somehow you got to remove the sand if you're going to use sand. So they have soft plugs. We look at soft plugs as a way when the engine freezes, you leave water and you freeze it, the soft plugs pop out. It's kind of an added safety feature that if you're lucky, it just pops the soft plugs out and then the water drains out. If you're not lucky, it just breaks the block. So that's not really why they're there. They're there for casting purposes so that they can cast it and they have a way of flushing the sand out and getting it out. We will remove the soft plugs if we're going to do an overhaul if we have a block that's really dirty, if it has a lot of calcium buildup and that kind of stuff, a lot of trash buildup or rust buildup, we can remove them. That gives us better access to go in there and try to clean some of that out. And so it's a nice handy access point, but its purpose originally was for sand casting. Storage at high temperatures. If you're going to build an iron block, they store it at high temperatures for several days, and that's to help harden the block and to heat treat the block. It relieves the stress and minimizes disorders. One of the things about iron is when iron is heated up and cooled really fast, it cracks. So anytime you're going to weld any kind of object that's iron, the only way to do that is to heat the whole object up. You can weld it and then slowly cool it down. Otherwise, if you heat a certain spot and weld it, it will crack. And so iron is really touchy about how you would actually repair it. And you can see this even in the building of it. They build it and they got to cool it down nice and slow, otherwise it cracks. It also stresses and twists really bad. So they may also treat it with inductive hardening, and we're going to see that again in a couple of places. Inductive hardening is when you pass electric current through a wire that's wrapped around. So they wrap the block in a bunch of heavy wire, run electricity through it, and that changes the molecular structure and makes it very strong. So they may be inductive hardened. So the disadvantages, they're very heavy. So they're big, thick, heavy blocks. You can see these ones on the table, or I mean, just picking them up, they're pretty heavy. They add considerable weight to a vehicle compared to other materials like aluminum or a sintered iron, which we'll cover. It retains heat really well. So you have a block that's really thick. Anytime the metal is thick, it's going to hold heat a lot longer. So if I'm running my engine and I shut it off and every half an hour I come back and run the engine, it might be nice to hold the heat in there so that I'm not getting a cold engine every time. But if you're putting this thing to work and it's just going to work for 8 or 10 hours in heavy heat, that would be a disadvantage. So for the most part, it's more of a disadvantage than it is an advantage. Repair, we talked about that. You have to preheat it. You got to preheat the whole block, get it all nice and hot. It's got to stay pretty hot. You have to use a special rod. It's got to have lots of nickel in it. You can weld it, and then you want it to cool real slow. You definitely don't want to be like throwing water on it, put it in a bucket. It's something that when you're done welding, you just put it someplace that's just let it, the cooler and slower that it cools, the better off you are. So you better know what you're doing if you're going to weld cast iron. It's a tricky experience. So torsional vibration, anytime you have an event that takes place once and then it's got to circle twice before it does it again, you're going to have torsional vibration. That's going to be caused the twisting action produced by the power impulse of the engine. So you're going to get this high pulse that happens, so boom, and then there's this, it's going to slow down and boom. So you get this twist that's going to take place in your crankshaft. And that's also going to translate into your block. The block's going to have these pulses that takes place, and that vibration, that pulsation is going to cause a lot of stress. And that block has to try not to fall apart with all that stress. So these stresses are rhythmic. They happen on a continuous, they're happening every constant basis. So it creates a vibration that you can put on a chart, and it's actually very consistent. But that vibration that goes through, a harmonic vibration, can stress something, just like taking a clothes hanger. You got that vibration that goes through, it causes that iron to work, can weaken the block. So blocks have to be able to compensate for that and actually withstand it. The top, this one here, this Duramax engine, they inductive harden just the top because most wear is done at the top of the cylinder. The bottom of the cylinder doesn't even have any wear at all. Nothing's even touching the bottom. So why put all that extra energy and electricity and stuff into the bottom? So they just inductive harden in the very top where it's the most critical. Lowest amount of oil and all the heat and temperature and all wear takes place up there. So it's common for them to kind of narrow in and just heat up or strengthen, harden, or put extra metal just in those places that they need it. And with the computer systems today where we can actually build a model and actually work it, they've been able to shave metal away in those areas we don't need it. So they can actually use animation to actually put stresses and figure out where it's going to fatigue without even building this thing. So they can add metal back and take metal away and shave lots and lots of time, money, and engineering and testing with those models. And so one of the things they've done is reduce the amount of hardening. Most of your wear is going to be up here, small amounts of wear here, and basically no wear at the bottom. And we utilize that as a technician as we're measuring. We're going to measure the top, measure the middle, measure the bottom, and then typically go below the ring pattern and actually measure it. And that's really what it was originally. And by doing that, if your caliper for some reason is off, what I'm looking for is how much difference between unworn and worn. And if my caliper's off, I'm still going to get that difference even if I'm not accurate as far as my real number. So that's why measuring it in 4 places kind of comes in handy. If for some reason you didn't have the right specifications in your book, or if somebody bored it or did something to it, I would also be able to tell you by measuring down here, this was standard, this is not standard. Someone's been into this engine before. Aluminum, Another type of material used in blocks. It's more common in your high performance diesels. Its biggest savings is weight, way lighter than iron will be. The challenges are going to be rigidity, strength, and reliability, because aluminum is softer. It can't handle the pressure. It's going to wear faster. It's not as rigid. It flexes pretty well. There's a lot of softness to it. So it doesn't have the rigidity, and it just doesn't have the strength. So trying to come up with material that's not going to give away is a challenge. So we do that, or we compensate for that in several ways. And one of them is they bolt the cylinder head and the main bearings. So the cylinder head itself, they'll put bolts that go all the way to the bottom. So we'll see a picture of that. Then we'll see some variations in the main bearings that help get more bolts in it to help add strength to it. Another major thing to get over these challenges is going to be the use of cylinders, steel cylinder liners. And so they insert it in and mold the aluminum around it. That way you get that wear, plus the aluminum still keeps the lightweight.
Very common to like a Briggs and Stratton.
We see them in our Briggs and Stratton. We see those in our any of the aluminum stuff that you have that's a commercial product that we want life out of it. They're going to see steel inserts of some sort. So only the real small disposable Briggs, Tecumseh, whatever brand that's just designed to only give you 50 to 200 hours is going to be a cylinder that's just aluminum. Anything that has life expectancy is going to have a steel liner in it, or some other kind of liner. So there's a whole bunch of other things that they've done too, but steel liners was the first and the most common one that we're going to see. So here's a picture of bolts. They take bolts, go all the way through, help hold the top and the bottom down, simply because we don't have enough strength in the aluminum not to rip the threads out. So it's trying to clamp it together. Here's another bolt design. Bolts go all the way through, so you got the head, the block, or the main bearing caps, bolt them all together and try to hold that stuff. We're not relying on the aluminum to try to keep it there. Aluminum, because it heats and expands so much, it's hard to keep our tolerances and keep it from coming loose.
So when it's, say those bolts are steel and our block and our head are aluminum, aluminum has a much greater thermal expansion rate than steel. So when it heats up, it's going to like stretch and tighten, and every time it cools, it's going to...
So the challenge for an engineer is knowing that they're different types of metals. What kind of bolt am I going to use? So they're going to have proprietary bolts that may have different amounts of alloys or stuff, and they know how much it's going to expand, the thickness of the bolt, how much it's going to expand. So they might use thinner bolts and more bolts or something. So they take all that into consideration, knowing that they expand. We can't use aluminum bolts and aluminum block. That's not going to work. So we got to figure out what's going to work. So it's a lot of challenge, and that alone you can see makes it difficult to have aluminum blocks.
Would the threads on those kind of bolts be like deeper?
The rolled style.
Yeah, like the thread.
It would be a rolled versus cut, like we talked about in chapter 3. They would be rolled because it would give it strength. And any fastener that's going to be critical like that, that's where you would find rolled versus cut threads. So that's going to be a special bolt. It may even look kind of strange, where it'd be thinner areas and thicker areas, so that it allows it to expand and contract. So
We wouldn't be able to pick that up at LNG.
not going to be picked up at our local hardware store. And it's not something that we typically find here. I mean, in all of the equipment that we've worked on, I've never had one that had bolts that went all the way through. So aluminum is most common in automotive world, not super common in this outdoor power world. Is it coming? Will we see more of it? I'm sure we will, but it's not super common. In the outdoor power world, weight is such a dramatic factor. You get a mobile or stationary application, stationary generators, water pump. That weight isn't a huge factor. In a car where we're traveling down the highway, and weight
Fuel efficiency.
is fuel efficiency and all that. All those pieces with weight control that you just mentioned, all those are a major factor. Weight becomes important. So we don't see it so much. If I was in the golf world and I don't want compaction, a fairway mower, yes, I might consider something like an aluminum block to kind of keep the weight down for compaction reasons. But remember, weight is also what gives us traction. So we kind of incorporate some of that weight in our traction. So it's kind of a give and take, and for the most part, it's not a major thing in most of our equipment. So we just don't see it. We'll probably see more of it as the technology improves above. We start getting blocks that are really strong, and the technology, then they'll start shrinking it and adding it in here. The third style is compacted graphite iron. And they take the engine block technique. It starts with powdered iron alloys, squeeze them into molds at high pressures, and heat them and bonds the metals together. So this is called sintered. Even in our gas engines, we have bearings that are sintered bearings. Briggs & Stratton use a lot of sintered bearings. And it's, when you look at them real close, it looks like really porous material. So if they take a little granular powdered iron, and they mold it, and then they press it. So they physically press it. We see that with plastic. They'll take plastic BBs and they press them together, and it's called sintered. And that pressing heats it up, bonds it together, but it's kind of porous, and it allows oil to get into that bearing surface and stay there. So rather than like a chrome surface where oil has to be on the surface, sintered bearing, they can actually put graphite and oils in there, and that, as it gets hot, starts drawing them out. So your engine runs out of oil. Instead of just running out of oil and being out of oil, it'll start pulling that lubricant out of the bearing and actually protect it for a while until you get oil back or something like that. So when I first start my engine, start it up, I'm not running dry bearings because the oil is in the bearing. So we've been using sintered stuff, even in this industry, for a long time. Now they're using it in the whole block. So they've kind of taken it to another level. It's 80% higher tensile strength and 45% greater stiffness than using an iron block, just a pure iron block. So that's a pretty dramatic numbers there. 22% less weight than iron with a 15% thinner walls. And thinner walls mean heat's going to transfer better. So we get rid of heat faster by having thinner walls, not maintaining that heat. And then less weight gets our fuel efficiency that we're looking for. There's a lot of really nice benefits from this technology. It's fairly new technology. It also absorbs sound better because instead of being this solid chunk of iron, it's got all these holes, this porous material that's not solid, so it's more like a sponge, and it absorbs some of that vibrations and that sound. So the engines tend to be a little quieter. Other things that we do to add strength to our blocks and reduce weight, we create deep skirts, cross-bolted ladder frames, and tunnel bores. So we're going to go look at these blocks here. The first one is a deep skirt. So this is an example of a deep skirt. This is a Mitsubishi engine. We roll it back. You can see that my crankshaft is on main bearings, but the main bearings are down inside, and the skirt actually comes down to the bottom of the main bearings. So this would be a deep skirt style. So the block configuration where the bottom edge of the block extends well below the crankshaft center line. And that one's not well below, but it's all the way down past the center line. And so that's going to give it strength. Cross bolted uses additional horizontally placed bolts to the crankshaft walls of the block into the main bearings. If this was cross bolted, what would happen is we would see bolts going into the side of the block, bolted into these main bearings to help add strength and rigidity. We're going to see that most often in aluminum blocks, where soft, we want to hold everything together, so they put the cap on, There's bolts from the side and then bolts from the bottom. Ladder frame, if we were to use a ladder frame on this particular block, what I would do is I would slide it in here, these main caps would disappear, and the ladder would be a single piece object.
Like a second block, bolting 2 blocks together.
Well, it would be a piece in here with all of the caps together. And because it's all one piece, instead of having individual main bearing caps, it would be all one piece that would go in, and I could bolt it on the outside and bolt it on the inside, and I would spread that stresses out and tie the block together in a lot of ways. And because it's going all the way across each one, it has the look of a ladder. If you took it out, it would have the main bearings and the end bearings, but it's all one.
But if one bearing went bad and scored one of the things, then you have to replace
You got to replace the whole ladder. Yes. So that whole, it's all one piece. The whole thing has to be replaced. So it's going to cost more money. So it's an additional block structure located between the cylinder and the pan. So it's going to be on that bottom part. And then the tunnel bore, which is like this green engine, has the highest strength and rigidity. The crank goes through the end of the block. So this is a Onan engine, and it has a tunnel block. And so here's the crankshaft for it. You can see the main bearing is independent of the crankshaft. We're going to take this block, or this engine crankshaft, and we're going to stick it in the end of the block. You see there's a giant hole there. So we stick it in. There's another plate that's somewhere else that bolts on here, so it'll look like this one, and that actually bolts into place. When you look at this center bearing, if I rotate it around, you'll see that there's a bolt here and there's a bolt on the other side. So this main bearing is actually a big giant piece that bolts together, so it's actually there. And when I rotate it, there's a hole here. Can you see that on the... So here's a hole. And that hole, when I put this in, there's a bolt that goes up through the center. That bolt will go into this hole and keeps that bearing plate from spinning. So it's held in place by another bolt that comes up through the bottom.
So how do you line up those bolt holes when you slide it in?
It's not super, when you slide it in, they slide in pretty easy. It's not pressed in or anything. So you slide it in, you want to get it fairly close to straight, and then you line it up, and you can actually reach into these side holes and kind of rotate it a little bit and drop it into place. And then, let's see if I can lay this down.
Yes.
Actually, this one goes in from the side. So this one is not coming from the bottom. Table. This pin right here is what goes into this hole.
Okay.
So that one's actually going to go in the side. So I would line it up, and then I would look in that hole till I could get the pin in. This particular one is not actually a bolt, it's a pin, and this pin has an oil passage. They're going to run oil, so I'm using the pin to keep it from spinning, and I'm also have a hole in the center of the pin, and allows oil to travel here and go in and actually lubricate the main crankshaft. So that one actually has a dual purpose for this pin. So I'm actually going to pin it and lubricate through the same pin. Kubota is another manufacturer that uses a lot of tunnel cranks. So the two Kubotas that we have on those little stands over there, if you took that one apart, it would be a tunnel design. And it actually has bolts from the bottom that hold it in place, and then they're using something different to get oil to it. So these are the 4 different kinds, and they're different ways of adding strength and rigidity to it without adding a bunch of weight. This first one here is a small horsepower diesel engine. conventional cast block, so there's no deep skirting on there. But then they take the oil pan, and you can see that there's webbing within the oil pan, and the oil pan itself is going to add the strength. Some oil pans are just tin, real thin, dissipate heat very well. Some are really thick and have lots of web structure in it and become part of the structure. In tractors, it's very, very common in tractors to have the oil pan itself be real thick casting, and that is an integral part of the actual frame of the tractor. So rather than having two side frames with an engine dropped in, they eliminate the side frames, and the frame is the oil pan. This particular one, you notice, has a lot of stuff sticking off to the side. We have a oil pan over here that came out of a reefer unit. So you're looking over the road trucks that have a cooler unit hanging on the front, and because reefer units spend a lot of hours on the road, the time between oil changes, to get the oil change intervals extended out, they put heavy cast iron pans in there with extra space to them to double and triple the amount of oil in them, so they can go longer between oil changes. So a lot of times they get left somewhere running for days and days, and then they travel around the country. People tend to forget about them, so they add extra oil. So we bought an engine, Yanmar engine, that had one of these kinds of pans on it. We put it into a John Deere Gator. In the Gator application, it was less than 4 quarts. So it wasn't even a full gallon. And the pan that originally came out of original was a reefer unit. That unit had like 2.5 gallons. So there's a big difference between the two pans. So we definitely had to remove them and replace them. The Gator had very little room for an oil pan. The oil pan had to be really small just to fit in the application where it was at. So a very small amount of oil. This is a deep skirt block. So just like the one on the table, the skirt extends way down here, and that's to add extra strength and rigidity to it. This one here has a plate, so this would be like the ladder style. And so if you look, this is the ladder here. Comes down, goes around, and it goes across. So it contains the main bearings, and it bolts on the inside. The oil pan itself is going to bolt here. So the rails for the oil pan are on the outside. This is a one-piece main bearing structure on the inside. It would allow me, if I wanted to, they could manufacture to put bolts in on both sides. So it's that other style where you have cross bolts. I could have cross bolts and bottom bolts. So if this was an aluminum block, I could add a lot of strength through that webbing in that application. Here's an example with those cross bolts. So if I had that webbing in there, then I could have bolts along the sides. They're coming in holding either the individual main bearings or that cross webbing, giving it strength, pulling the side walls into the main frame and just bolting it all together. So this is that ladder frame again.
So that's like the bottom part bolts up.
So we have a pan that's bolted to the outer ridge, and then this main bearing girdle, as I talk about a girdle, this is a piece here. This one is actually, instead of slipping on the inside, this ladder one actually goes all the way to the outside. What's the disadvantage of this? What would you see as a problem with this particular style? Anything jump out?
Well, if you have one bearing replaced, you have to replace the bottom half of the block. And you have to have passageways going through it for your coolant and oil lubrication.
Now coolant is not going to be down there. So the coolant only comes, you got your little soft plugs up here. The coolant is actually going to end somewhere in this area. Right at the bottom of the cylinder, there are no more cooling jackets below that. But I might have oil. So some kind of oil passage, I might have to have drilling passages for that. I may or may not. I may be able to drill them inside and solve that problem. So it depends on the manufacturer. As a technician, every single time I add a cover, a plate,
Add a gasket.
I have to add a gasket or a sealing surface. And so the disadvantage, one of the disadvantages, it's another sealing surface. I've got this gasket that's between there, or we put, form a gasket, liquid sealing in there. Anyway, anytime I have this surface come together, I have to have some way of sealing it, and that's another potential leak point. So we have a John Deere tractor, lawn tractor out here right now, and the reason why we're going to pull it out is because the oil pan, the crankcase cover, which is part of the frame, is leaking, and there is a cooling passage in that particular one that passes between that surface, and for some reason it's leaking, and we got to pull the whole engine, pull the whole cover off just to put a new gasket in there and put it back together. So anytime I have one of these surfaces, it's a potential future problem. So that would be a problem there. So here's another ladder frame design. So this is a picture before it. This is without the pan on it. And so you have this seam that's here, and now we have a seam that's here. So we have two potential leak points. But you can see how we can have lots of bolts holding this thing together. So we have bolts down here holding that ladder frame to the engine block, and then we have bolts that'll go through that ladder frame into the main block too. So lots of fasteners holding this whole thing together.
The Ford 6 liter.
So it's a pretty new, the 6 liters not that old, pretty new system. Just a lot of fastening for the technician. There's a lot of pieces to it. When you take it all apart, kind of elaborate that is. We spin and we damage this main bearing. We're replacing a lot of money there. So tunnel bore. So we showed you the one on the table. You can see it's got very large main bearing supports, and there's a giant hole in the end, so the whole thing slides in and then it's bolted, so your thrust surfaces are in this outer main bearing support. But because the block itself is solid, everything is rigid around, there's nothing bolted, you got this big block with this crank that slides into the middle. It adds a tremendous amount of stability and strength to it. There's no flexing because there's nothing to flex, it's all one piece. So it is a very rigid, high strength, and a very smooth engine. Talking about smoothness, we're trying to balance it. Every engine needs to be balanced. We're always trying to remove that vibration. There's a primary balance. Primary is achieved when the crankshaft counterweights offset the weight of the piston and connecting rod assembly. And so we'll zero in, look at this crankshaft right here. This is the crankshaft that would go in this engine. And you notice we have counterweights right next to where the piston is going to connect, and then you see holes drilled in it. So this engine is balanced, they spin it, and then they start removing metal to get it to balance out. So we have counterweights, and then we drill it to balance it out. So we have multiple ways. This one down here has 4 drill holes in it. This one doesn't have any. That one only has 3.
Essentially add a little bit extra metal to the counterweights. That way they know that the heavier end is going to be on the counterweight side. They don't have to drill anything out of either side.
So it's easier to remove it than it is to try to add it back on. You can't weld on it to add weight. So we can remove it by drilling pretty easy. So they add a little bit extra and then balance it out. This one here also has big heavy counterweights that are opposite of the connecting rod. So that's the first one, our primary balancing is done right on the crankshaft itself. And you notice that they don't put it on one side, they put it on both sides, so it's nice and even. Sometimes in the gas engines you'll see where the counterweight's really on one side. Less vibration, less force because you have less compression, and then the torque out of a gas engine is not as much. So our counterweights are a little bit sloppier, a little bit less, lighter. In a diesel, it's very critical. So we have it on both sides, they're fairly even, and we're trying to keep them balanced. So that's your primary way. Secondary things, there's a lot of different secondary ways. One of them is by having more than one cylinder. A single cylinder diesel engine it's going to have some pretty serious counterweights to help counteract that vibration, because you just jerk this thing one way and the other, and it takes a lot. So at least having 2 cylinders helps a little bit, but even a 2-cylinder is rather unbalanced. It's really hard to get a 2-cylinder engine without lots of counterweighting to be smooth. You get to 3 cylinders. 3 cylinders are inherently smooth. Most 3-cylinder engines don't have a lot of extra counterweights in there. You notice that this is a 3-cylinder engine here. This is the crankshaft. So it's got some counterweights on the crankshaft, but not like a tremendous amount. And you don't see any other secondary counterweights bolted into this engine to kind of help smooth it out. If this is a 4-cylinder engine, 4-cylinder engines are not very well balanced, and it will be very common to have secondary shafts in here rotating to help smooth them out. 3-cylinders don't have that. So that's kind of one of the reasons why we see so many 3-cylinder engines in this industry, is because of how their balance is. Not as balanced as larger cylinders, because you get into more and more cylinders, easier just to balance them out. But as far as the small diesel engines, you almost never see a 2-cylinder. We rarely see a single cylinder. And then the 3-cylinder is the most common. Once we start getting up in horsepower, then we're going to jump to a 4-cylinder, and then from there to a 6-cylinder. European engines, we're going to start seeing 5 cylinders. Mercedes and Volvo, I think it is, they have 5 cylinders, because there's a way of balancing it out. So movement of one piston counteracts the other, so multiple cylinders. Block design, whether it's a opposing, V block, or inline, we can use the block design to help balance it out. So opposing cylinders, the forces go opposite each other. We're going to use that to smooth them out. And opposing is very balanced. But you start laying those cylinders down, we put oil in the bottom, you tilt it on a hill, oil runs into the block. We have other challenges with that. So we don't see a lot of opposing cylinders. Same, just like in the gas engines, we don't see a lot of opposing. Most of them have kind of brought them up so oil keeps running out of the pistons. Firing order. The order that we fire the piston is going to help balance it. You never see it go 1, 2, 3, 4. 1, 2, 3, 4. They don't just start in the front and start firing. They balance them out, the firing order, so that the engine forces are spread a little more balanced, a little more evenly, and help balance it out. And then we already talked about number of cylinders. So this is an inline 6-cylinder. So you can see here we have pistons that are traveling up and down. The closer together each piston is to firing, the smoother it's going to be. So you can see as we get to a 6-cylinder or an 8-cylinder, we can start bringing the time between firing, combustion events. We bring those closer together, it's going to be smoother. So that becomes a good secondary balancing system. Blocks themselves, we get into the cylinder, we have three major kinds of blocks. One of them is a parent block. We talked about that a little bit last one. That means that there's no sleeve in that block. Most of our gas engines are parent blocks where it's all cast as one. If something's bad, you'd have to bore it and do something with it. So advantages, lower initial cost. You just have one item. You don't have a bunch of extra seals and all that kind of stuff, so the costs are down. Cylinder itself adds structure because the cylinder is molded as part of the frame. Everything is bolted, or not bolted, but everything is molded as one piece, so it's going to be stronger. It's compact and lightweight. I don't have a bunch of extra pieces in there to allow me to slide this together and connect it together. Disadvantage, you have to rebore it. If it gets scored, you score the cylinder, you dirt it out, and it gets worn, you got to rebore that engine. And to do a rebore, you have to completely disassemble it. And you can't just leave extra bolts and stuff hanging out. When they take it out and put it in their machine, they want that block as as bare as possible so that they can actually put it in and bore that thing out. So it's a lot more time consuming when it comes to time to rebuild it. Now, stepping forward in today with today's emissions, we already talked about the fact that if you're going to rebuild an engine in today, it has to be 100% back to manufacturer specification. Well, reboring is not going to be possible if you're going to bring it back to manufacturer spec. You'd have to use a liner or something that would bring it back to spec. But they're also looking at all the other things that you have to bring up to spec. If we can make the engine cheaper by using a parent block and making it more rigid, and we can make it more emissions friendly, then the cost of just replacing the engine versus rebuilding it is going to be a better option. And so you'll see more manufacturers look at, hey, you as a technician cannot get everything back up to 100%, so we're going to make it to where you cannot rebuild our engines. You dirt it out, you score it, you're just going to replace it. And they're just eliminating those initial costs that they have and extra material which adds to the structure, and say it's not rebuildable. And I think you're going to see more and more of those engines out there. So I think in the larger engines, you're still going to see some stuff that you can rebuild, but the trend is coming. The engine goes bad, you bolt it, you unbolt it, you send it off to a company that rebuilds them, and they send you a new one. And they're going to be doing whatever it takes to make it 100%. And because it's so critical, you just don't have the tooling to do it. So you're going to see less and less of it. Wet sleeves. Wet sleeves are these piston liners that we see here on the table. Direct contact with the coolant, easily to replace. Pop them out, pop new ones in. And because the liner itself is just an individual piece, it's real easy for a manufacturer to do inductive hardening or whatever it takes to make it really durable. They're pretty strong, machine them pretty easy because you can handle them pretty easy, unlike a block that you're trying to spin around and do whatever. And so it's pretty easy to actually create something exactly like you want with a liner. The disadvantage is coolant leaks. And so the bottom of that liner has to have some sort of seal, and usually it's some kind of an O-ring. If you run water in it, you'll see where that O-ring goes. That O-ring will have pitting around it, and if the block gets pitted where that O-ring is, it's going to leak. And when it leaks, where does the coolant go? Goes into the oil. So here's one. You can see this one has 2 O-rings, and so the O-ring is actually grooved right into it. If there's some kind of leakage, it's going to leak right into the oil. So you pull your dipstick and you're like, where'd that come from? Well, one of the options is going to be this O-ring. This other liner here that we have, this one is smooth. The O-ring sits in the block. So either way, I don't have a lot of options. If it starts to pit in the block, I'm going to have to replace the block. So that one I could have pitting in the block, and I'd have to replace the block. So either way, that's the biggest challenge, is keeping that out. How do I prevent that pitting from happening? Keep your coolant changed. So when that coolant itself, most coolant is 3 years, you should replace it. We have extended life coolant now that goes up to 10 years. There's test strips that we can test it to see if all the additive package is good. Most people check antifreeze to see if it has a low enough freeze point, and that's it. Well, there's a freeze point and a boiling point. Both of them are critical, and then the additive package is super critical. So we already looked at them in the last chapter with the pitting from the cavitation corrosion. That additive package is what prevents that. And it's the same thing that's going to prevent the O-rings from having problems. So looking at our blocks, where does the heat? The very back of an engine, furthest away from my water pump. Water comes from the radiator, goes through the water pump, goes into the front of the block, goes through the back of the block, and circulates and comes back out. So the back of the block tends to be hotter. If you overheat an engine, you're going to see more damage in the back of the block than the front of the block. It depends on how much restriction it is, how much trash is built up on the cylinders and in the block. And so I'm going to be looking in the back and expect more damage in the back. So this is just an example of a Cummins with a parent block. So this is the two examples. Wet liner is O-rings at the bottom, and we have coolant directly in contact with it. The next one we're going to talk about is going to be a dry liner, and that's where the liner is inside of the block. So I have a cast block, and then I press a sleeve into that block, and it's a dry block. The liner itself is not touching the coolant, so I don't have to worry about any kind of cavitation corrosion, and there's no O-rings for it to leak. The disadvantage is going to be, or advantage, yes, it's replaceable in those two items we just talked about. Disadvantage, slow heat transfer. We're trying to actually put this coolant or the heat transfer out into the block. It's harder to do that. It takes more time and more steps to machine, and it weighs more than a parent block. So that's a disadvantage. Crosshatch, just like gas engines, we need to have some kind of crosshatch. That's what holds the oil up there at the top. So we have a 45-degree crosshatch as our most common crosshatch. That's the same in gas and the diesel. And if we don't have it, it's going to be a problem. They talk about in your book using another type of crosshatch that goes in and polishes it up. I've never seen it or used it. So we just want to make sure there's a crosshatch. Cylinder wear. Greatest amount of wear is at the top of the cylinder because we don't have as much oil. And if you don't have a crosshatch, you won't have the oil. You're going to have more wear. So it's important that you always have that crosshatch. So they have honed, which is what we use for our crosshatch. And they have this one called plateau. They use some kind of bristle brush, smooths it out a little bit. I've never done this. I've never seen it. I've never heard it. So it's something fairly new.
It improves the braking time.
Correct. We're going to get into the cylinder. Well, I talk about wear. So with diesel engines, our crankshaft, our crank throw are longer because we have longer strokes. As you extend this out and get more throw, we have more stresses on our crankshaft, but we also have more side thrust on the piston. So the piston itself is going to be thrusting minor and major thrust on both sides of the cylinder. We're going to see a lot more wear on that cylinder liner due to the fact that we have longer crank throw. Crankshafts, I think we're going to have to stop there because we're going to stop. So we'll have one more session and then it's going to cover crankshafts and then we'll finish this chapter.